In this video, we'll explore some computer science theory and dive into the fundamentals of computational complexity. Let's get started. The computational complexity of an algorithm is a measure of the amount of resources, such as time or space, that is required for an algorithm to solve a problem, usually measured as a function of its input. In other words, computational complexity measures how the resource demands of an algorithm scale with the input size. This is a purely theoretical framework for understanding different algorithms, free from any implementation details or hardware considerations. We usually express complexity in terms of big O notation, which some of you may be familiar with in other settings. In this case, big O notation mathematically describes how the resource demand of an algorithm will scale with some input size, usually denoted with the letter n. Understanding big O can be a little bit challenging without looking at an example. So let's take an example implementation of an algorithm which sorts an array of numbers in ascending order. This algorithm is called bubble sort because it bubbles up the largest number to the end of the array on each pass of the for loop. For this video, you don't need to understand how this algorithm works. All we want to do is analyze how the resources required to execute this algorithm scale with the size of the input. In this case, this algorithm deals with an array, and this array will have n elements inside. Before we start analyzing this function, we need to ask, what are we actually trying to measure? In this algorithm, the main resource that we care about is computational time. This implementation doesn't require any additional memory other than the memory needed to store the input array. So let's try and estimate how long this function will take to execute. For now, we'll assume that we don't know which hardware we're going to run this algorithm on, so instead let's try and work out a functional expression for the runtime that should be proportional to the execution time, that is also based on the input size n. Let's go through each line in this algorithm and write down an estimate for how long it will take. The first line simply queries how long the input array is. This array is a data structure and will know how many items are stored inside, so this is likely just a read from memory and will operate in constant time, i.e. it doesn't depend on the input size n. Let's denote the runtime of this line as a, which is just some arbitrary constant. In the next few lines we have a nested for loop. It will be easier for us to understand this runtime if we start from the inside and work our way out. Let's focus on this if block at the center of the nested for loop. The time taken to execute this statement will depend on whether the condition is true or false, but for a given input array this is likely to be some constant time operation, as reading to and writing from an array is a constant time operation. For this reason, let's label the time taken here as some constant b. Now let's take one step back and look at the inner for loop. This for loop iterates over the numbers from 2 to n minus k. As k itself goes from 0 to n minus 1, we can estimate that this loop will execute approximately n over 2 times. As we know how many times the loop executes, we can combine this with our constant b that we calculated earlier, which defines the runtime of the inner loop body. When combined, this for loop will likely contribute b times n over 2. Now we have one more for loop to deal with, and that's the outer for loop. It's pretty easy to see that this executes n times. We know that the inner loop will execute in b times n over 2, and we know that this executes n times, so in total our contribution to the runtime for this for loop will be b n squared over 2. The last statement in our function will just return the results itself, and this will also execute in some constant time which we'll call c. Now that we've analysed every line of code, what we can do is combine these estimates together into a single estimate for the total runtime of our function. This expression depends on n, which is the length of the array that's passed into this algorithm. We also have some arbitrary constants a, b, and c, which will depend on the actual implementation details themselves, so what language the algorithm is written in, and also which computer it's executed on. Since these constants are mostly arbitrary and will change from machine to machine, they're not incredibly useful at describing some fundamental properties of this algorithm. We want to be able to classify the resource usage of this algorithm independent of any implementation details or particular hardware that the algorithm runs on. For this reason, we often try and distill our runtime expression into something a little bit more generic. In our expression, we have a few arbitrary constants that we can actually combine together. So for example, a and c can be combined into a new constant d, and b over 2 can be combined into a new constant, which we'll call f. This combination doesn't get us too far, but what we can do is further distill our expression. If we care about scaling, we can ask what happens when n gets very large. In this case, the first term will dominate, regardless of the relative size of f and d as constants. If you imagine n as being 10 to the 6, then n squared will be 10 to the 12, which makes it very unlikely that the constant will actually contribute to the overall runtime in any meaningful way. In effect, this means that we can actually just get rid of this constant. Now that we have a single term, we know that the runtime is proportional to some function that grows quadratically. A more succinct way of writing this is expressing this function as O of n squared, which means that the runtime should scale quadratically with the size of the input. This is a very generic statement, and it doesn't depend on any implementation details because we've implicitly got rid of any terms in our expression which are dominated by n squared. We've also got rid of any of the constants that might make our runtime value less specific. This big O notation here specifically describes the upper bound of some runtime up to some scaling constant. This idea is easier to demonstrate in a graph. So let's take our bubble sort algorithm and time how long it takes to execute on average with random arrays of varying lengths n. Here I'm plotting the time taken versus our input size. So now that we've got actual data for a runtime, let's see what it means for this algorithm to have an average time complexity of O of n squared. What we mean in particular is that there is some function, which is a constant times n squared, that provides an upper bound for our runtime. Here we can see that we can reach a constant of around 1, which provides a bound for our runtime in the long n limit. We can also perform a similar operation to try and find a lower bounded runtime for our algorithm. Again, we'll choose the same form of a constant times n squared and reduce this value until we can find a clear lower bound for our runtime. And a good choice for this value is around 0.2. These two functions provide upper and lower bounds for our function. You will see big O notation when we're trying to define the upper bound of a function. When we're talking about the lower bound of a function, we usually use the notation omega instead. Both of these notations are closely related, but the distinguishing factor is whether you're talking about the upper bounds of a function or the lower bounds of a function. One thing to know about this big O notation is that really we're describing sets here, and so technically we could use any function which bounds our observation. In this case we could use n cubed or n to the power of 4, which would still be valid big O notation for this problem. However, it's usually best to use the tightest bounds that we can to accurately describe our function. One more important caveat about computational complexity is that we only need to prove that something is eventually bounded. If we find a function that bounds our function for large n but doesn't bound it for small n, it's still a valid complexity. To give an example of this, let's change the scale to a log-log graph. Using a log-log plot helps us visualize how our data changes across several orders of magnitude in both our x and y axis. One thing that we can see in this view is that our upper bound function actually intersects with our data. This is actually completely fine, and all that we need to do to satisfy a upper bound is to know that it eventually bounds our data. This idea of being eventually bounded is important because it reinforces the idea that big O notation is only really accurate for describing how a function evolves in the large n limit. Later on in this video, we'll see an example of how big O notation breaks down at smaller values of n. Now that we have some idea of what big O notation actually means, let's look at some common complexities that come up to describe a variety of algorithms that you might see day to day. The first complexity describes constant time algorithms, which is usually denoted as O of 1. An example of this could be reading a single element from an array. Next of all, we have O of log n. These types of algorithms are usually quite efficient, especially when n gets very large. This runtime usually relates to algorithms that involve the tree data structure. So for example, searching for an item in a binary tree has O of log n time complexity. The next scaling is very common. This is O of n, which is linear scaling. One example of an algorithm which scales linearly is trying to find the maximum element in some unsorted array. It's usually quite easy to identify when an algorithm is O of n because you'll see a for loop that iterates through each element in an array. The next runtime, which you may commonly see, is O of n log n. I won't say too much about this complexity as we'll be going over an example later on in this video. The next setup is the O of n squared family. We've seen already that this applies to bubble sort, but you can usually identify O of n squared algorithms by trying to find nested for loops in your code. If we move past the rest of the polynomials, we have exponential complexity. It's not often that you run into algorithms that have exponential complexity, but these problems tend to be quite hard to solve. You might see these sorts of exponential runtimes when you're trying to write algorithms that simulate a quantum computer classically, in which case the algorithms usually scale exponentially based on the number of qubits that you're trying to simulate. One important factor here is that the base is actually important. When we were writing our big O notation before, we were getting rid of constants, but we can't just change the base in our exponential. So for example, O of 2n is not the same thing as O of e to the n. Finally, the last example I'll give is a factorial runtime. This is usually the worst type of runtime that you can encounter in day-to-day algorithms, and it usually comes up when you're trying to write an algorithm that iterates through every possible permutation of n items. Here I haven't included every possible function that you're likely to see, but this hopefully gives you a flavor of how the different functions will scale with some input size, and which terms will dominate other terms when we start combining these expressions together. So here's an example function that we can use to try and practice calculating our total complexities. We'll go through this function line by line. On the first line of this function, we're calculating n, which is the length of the array. Again, this is a constant time operation, and we'll keep track of the current big O notation for our function in the top right hand side of the screen. If we look to our next line, we're calling a function that has complexity O of n. If we combine a function that has complexity O of 1 with a function that has complexity O of n, we'll get a total complexity of O of n, and so we'll update the total complexity for our function in the top right. The next few lines of code focus on a nested for loop. So let's go directly to the center of this nested for loop and work our way out. In purple on the right, I'm keeping track of the current complexity of the lines that we have selected. Within this for loop, we're calling this function h, which is denoted as having complexity O of n. If we move to our outer for loop, we can see that this function gets executed exactly 10 times. However, the number of executions doesn't scale with n, so the total complexity of this entire for loop is still O of n. We can look up to the previous line and see that this line has a complexity of O of n squared. We can combine O of n squared with O of n to get a total complexity of O of n squared, and that's because the O of n linear term is dominated by the n squared quadratic term. Finally, we'll move up to the outer for loop. We can see that this executes a total of 2 to the n times. Since the number of executions depends on n, we need to factor this in when we combine it with our O of n squared estimate for the runtime of the loop body. The way that we do this is just multiplying n squared by 2 to the n. Now that we've calculated the complexity for our for loop, we can combine this estimate with our previous estimate of O of n for the previous lines of the function. Since 2 to the n times n squared will dominate O of n, we can update our complexity to be 2 to the n times n squared. Now we only have one line left in our example algorithm. In this example algorithm, the variables x, a, and c are all scalars, and so this line would also execute in some constant time. Since this constant time operation is dominated by our current expression 2 to the n times n squared, we can actually ignore the contribution from this line and finish up. So now we've gone through every line of this code, we can conclude that this function should execute in O of 2 to the n times n squared. So this is a super exponential runtime. So now we've got some experience with computational complexity and we know how to deal with big O notation. But let's see how we can actually use it to compare two algorithms together. As we've already seen the bubble sort algorithm from before, let's look at another algorithm which also performs sorting in the same way. This algorithm is called Quicksort and it's fairly simple to implement, but it uses recursion. This algorithm chooses the midpoint of an array and uses that element as a pivot point to produce two smaller sublists containing all of the elements left of the pivot and all of the elements right of the pivot. These two sublists are sorted using the same function recursively. The base case is when there's 0 or 1 element in an array, in which case that array is already sorted. Once all of the sublists are sorted, they can be concatenated together in the correct order. We won't prove the complexity of this algorithm in this video, but if you want to have a go at working it out, you should start by assuming that the left and right splits will be roughly 50-50 on average. Pause the video now if you want to give this proof a go. Okay, if you've had a go, you should have found out that this algorithm has an average time complexity of O n log n. You can also consider the case where the left and right lists are completely unbalanced, in which case this algorithm actually has a worst case time complexity of O of n squared. So now let's compare this algorithm to bubble sort. We saw before that bubble sort had a complexity of O of n squared, whereas this new quicksort algorithm has complexity O n log n. So based on this complexity alone, which one do you think will be faster for a given input? I would encourage you to make a guess now. So let's find out which one is faster. So here I've timed the execution of these two functions across a variety of different input size, and here are the results. You can see on the graph that bubble sort was much slower than quicksort for the same sized arrays. This should be somewhat unsurprising because we know that n squared grows faster than n log n. And so the complexities of these two algorithms implies the performance as n gets much larger. One thing that you should know is that there is a huge caveat, but we can only actually see this caveat if we switch to a log-log axis again. On this scale, we can see that our bubble sort implementation is actually much faster for smaller input arrays, and quicksort only really pulls ahead on larger arrays bigger than a few hundred. This is one point that I really want to emphasize, and that's very, very important when we start talking about high-performance computing. Computational complexity describes only one aspect of an algorithm, and it doesn't take into account how efficiently that algorithm has been implemented or the hardware that that algorithm is running on. This is something that can be overlooked when we're discussing computational complexity and comparing various algorithms. Just because an algorithm has a more favorable complexity, it doesn't mean that that algorithm will be faster than other algorithms with less favorable complexities. The information that we drop in big O, such as the constants or the non-dominant terms, are actually very important for predicting the actual runtime of our function. This means that it's not enough to just choose the algorithm with the best complexity. You actually need to make sure your implementation is efficient enough to get the runtime that you actually need. For the most part, computational complexity can help guide your choice of algorithm. If you have two algorithms that achieve the same task, but one of them has a factorial complexity and the other one has a polynomial complexity, you can be pretty certain that the factorial implementation would be a lot slower than the polynomial implementation. This measure does not always tell you everything you need to know about your algorithm's performance. For a more complete picture, you actually need to measure the performance of your algorithms and make sure that they are implemented efficiently. For this, you'll need to apply some theory and best practices to help get the best performance out of your code. In the next few videos, we'll learn how we can perform experiments to analyze the performance of our algorithms, and we'll discuss techniques for improving the performance of our code.